So a few sort of logistical things to talk about before getting back to talking about physics. Number of people talk to me in questions and stuff about various things. First one is the homework site. It is this, it runs under Moodle. I'm running it myself off of one of my own web servers. And so the address is on that printed syllabus. It's on the website for this class. It's just moodle.bloomfieldweb.com. And if you didn't get an email from that site with your username and password, or preliminary password, temporary password, you can get it anyway. And that is go to that website, again, moodle.bloomfieldweb.com. And your username there is just your mail handle or computing ID. And your email is your UVA email. So mine, I'm lab3e@virginia.edu. So my username is lab3e, and so on. And you can get it to send you a new password, I'm pretty sure. It may take at least a minute. Give it at least a minute to send you the stuff. It may go into your junk, your spam filter stuff, but chase it down. It takes a minute or so to send out emails just because of the mechanism that runs within the website. What else about this? Any questions about getting onto that homework site? Again, it's free. I'm just running it. The problem sets. The first problem set, problem set 1, is due on the 12th. So Wednesday, a week from this Wednesday, at 1, like right at the start of class. Again, don't shoot at it, shoot before it. You get one grand try at the problem set. That's one attempt, it's called. But you can try the questions multiple times, twice. You get the second chance you can submit once, and it'll tell you, it'll give you feedback. You either get it right or you get it wrong. If you get it wrong, it'll tell you a bit something. And then you get to do it again for half credit. And if you make choices tentatively and want to leave and come back, you can leave and come back as many times as you want. If you wanted to save your tentative choices, those unsubmitted ones, I think you have to press finish attempt and then do not actually, you press finish attempt and then it will say, do you really want to be all done with this and turn it in forever? And don't do that. Don't do that until you're really done. Okay? Any questions about homework stuff? If you get, as you work through them, and if you get stuck and stuff, don't just get stuck in a vacuum where you just give up. Talk to each other. Talk to me. That's why I have office hours, among other things, is to talk about these questions, because that's where you learn the material. The intention is for you to learn it, not to just be frustrated by it. Anyone on the waiting list, come and talk to me after class. What else? I've tried to set up the main schedule for the class on the class website. Now has the suggested reading for the day. This is before the day. Reading the lecture video, again before, and the lecture slides that I at least mentally use in preparing the lecture video. So you can see all that stuff. You can print out the slides, bring them here if you like, whatever. After class, I will post. I'm posting the video right there. I'll post it after class, and I'll also post the question slides that I've been using with the iClickers, including lots of questions that I never get around to asking. So we'll see. It's all a work in progress. Anything else that I should think about? We want to think about questions? Please keep asking the questions. The text over there, you can text me over there on the left side, and the email. When you go to Moodle and you ask it to send you a password, it may take a few minutes. If it really doesn't send it out, talk to me or write me an email and we'll figure out. I'll double check, make sure that aspect of the website is working. It should be working. It's possible that UVA is eating emails from me or my website. It's been a running battle, but try to get past all the spam filtering and non-spam filtering. It's been a battle for years. Okay, they're not aware that it's a battle. I'm the only one. It's a tempest in my teapot. Okay, so before going on to the next topic, which will be falling balls, I just want to make sure that I've that you're all comfortable and on board with a few details from a few physics issues, from skating. I mean, things. It's nice to put the video up of the lecture up there and just assume it, but I don't want to assume it too completely. So I want to make sure you're all comfortable with the 5 physical quantities that I introduced on the lecture video, or equivalently in the book. And just to remind you what those are: position, velocity, acceleration, mass, and force. Okay? So just a 2-sentence summary of that. Position is where you are, and we use it from time to time. It's if you're trying to describe the real world and where things are and what they're doing, you need this physical quantity known as position. And unlike the simple quantities that you're used to in, say, when you're cooking something, where 3 cups is a perfectly good physical quantity, we all can agree of 3 cups of water is a certain amount. Position is a vector quantity, has direction to it. And if you don't specify the direction, you haven't done this, you haven't finished the job. Where am I located? I'm located 6 feet from, 6 feet from the computer monitors. 6 feet, well, this is 6 feet, so is this. How do you distinguish them? You got to put a direction component in. So position has a direction as part of its intrinsic being. So I'm 6 feet away, I'm 6 feet south of the computer monitors. Now we've pinned me down. Any issues with or concerns about position? The next quantity I introduced was velocity, which is how your position is changing with time. And whereas you can see position with a single glance, you can see velocity with 2 glances. You have to look once, look again. You knew that I moved. My position changed with time, so I had a velocity that wasn't 0. And in particular, I seem to have moved about 3 feet or maybe a meter. Over the course of 1 second, my velocity could be described as about 3 feet per second. Again, direction matters. So it's not 3 feet per second to the left, it's 3 feet per second to your right. That's velocity. And to distinguish velocity from speed, speed is the amount of velocity, but doesn't tell you which way you're going. This is again 3 feet per second. So is this. Okay? No direction to it. Velocity has the direction part. In common language, they're used sort of carelessly. They're carelessly interchanged, speed and velocity. Speed is normal, and velocity is when you're trying to be highfalutin or something. I had a velocity of such and such. Yeah. All right? But for physicists, it actually has that added bit of direction to it. Any questions about velocity? For those of you who have taken calculus and want to think a little bit about that, so those of you for whom calculus is anathema, plug your ears. Velocity is the time rate of change of position. It is the time derivative of position. So we won't do any of that calculation, but that's where it is. Third physical quantity, acceleration. And this is the one I want to dwell on for a little while because it's tricky. Acceleration is subtle. Acceleration is the rate at which velocity is changing with time, and it takes 3 glances in concept to see it, because you got to look for the velocity twice. So if I'm walking along steady, my velocity is not changing with time. So my acceleration there was 0. Okay? But if I was speeding up in the direction I was going, so I had an acceleration that wasn't 0. I was accelerating to the right. As you look, glance after glance after glance, if you look at them, if the glances were at equally spaced in time, I was covering more and more and more distance. So my velocity was increasing to the rightward direction. I was accelerating to the right. Again, it's got a direction to it. Questions? this is an aside. The homework assignments will all be on that website, nowhere else. You have no other outside work required except those problem sets on that website, apart from the exams, which will be in this room at class time or during the final. Okay? Rolling back then to velocity and acceleration. So I'm going to show you, I'll play human animation, as is my, my tradition here. I'll show you my acceleration with my hand. And watch what happens as I do various accelerations. So I can have a velocity without an acceleration. The velocity comes with my history, what I was doing moments ago. So if I'm already moving to the right, I don't have to accelerate in order to keep moving to the right. I do it naturally, that's inertia. But if I accelerate, this is me accelerating. I'm going to stop, otherwise I'm going to go too fast. You see, my velocity changes as I accelerate. And it changes in the direction I accelerate. It doesn't mean I immediately move in the direction I accelerate. It means that, now I'll stop because I can't chew gum and walk at the same time. The acceleration shows you the way in which the velocity is changing. It has a history, so it doesn't immediately forget I don't forget that I was heading, say, to your left, and if I start to accelerate to the right, I begin to lose my velocity to the left. Gets slower and slower and slower and slower. Momentarily it's 0, and then I start picking up more and more velocity toward the right. As you're sort of pouring velocity into me toward the right. Is that okay? And you notice, when velocity and acceleration are in the same direction, and they do not have to be, your acceleration is in the direction things are pushing you. In fact, the net force on you causes that velocity, causes that acceleration. If I am accelerating to the right, meaning something's pushing me to the right, and it's real, there is, the floor is going to do it. It's me and the floor negotiating. We're figuring out how to get this to happen. And I can accelerate to the right. Here I go. Okay, stop. So during that time, the floor was truly pushing me to the right. If you played floor, you would notice that you're actually shoving on me. I made you do it. And I accelerated toward the right. I picked up speed, and that's sort of the simplest of the accelerations. It's the one you're most familiar with. It's like when you're at a light driving a car and you press the so-called accelerator pedal. You really do accelerate forward. So you want to go forward, which let's say to the right. You press the accelerator, you accelerate to the right, your velocity is to the right, everything's simple, and you go faster and faster. Familiar kind of acceleration. The weird one is when you're moving to the right, red light, you slam on the brakes. You come to a stop. The brakes actually caused you to accelerate too. It's just the acceleration wasn't forward, it was backward. You slowed down. You okay with it? Questions about that idea that you can be moving to the right but accelerating to the left? And when that happens, you slow down. You lose your rightward velocity. So brakes are effectively an accelerator as well, just one that slows you down. And there is a special name, a commonly used name, for this one special case of acceleration where you're accelerating opposite your velocity. It's called deceleration, just to give it a name. So that's all deceleration means. It's a special case of acceleration. The more general term, which I'll use almost exclusively, is just acceleration. Any questions about? Is acceleration a vector quantity? Absolutely. It has a direction to it, and accelerations are caused by force, net force. So for me to accelerate to the right, I need a net force to the right. That means that all the forces acting on me, and the forces individually, you all can come and fight over me, pulling me apart or pushing me together. But if you all push me in a way that together you shove me to the right, I'm going to accelerate to the right. So you overall exerted a net force on me toward the right. That's the direction I'll accelerate in. So both force and net force have direction. They're vectors also. And the acceleration is a vector quantity, and it's in the same direction as the force. So if you push somebody to the right, they don't accelerate toward, up. They accelerate to the right. Okay? So my biggest well, one more physical quantity, and then I'll come back. Mass. When you push on different things, they accelerate differently. So you push on something little. I mean, a little ball. Give it a certain push. Boop, off it goes. It accelerated during the moments that I was pushing on it. It accelerated quite rapidly toward the left because I pushed it toward the left, and off it went toward the left. Do the same thing with a bowling ball. You know, of course, I'm just going to hurt my finger. I mean, I'll do it sort of. Okay, it's no fun because I gave it the same shove for the same time and all, but it didn't accelerate very much. Why not? Because it has this enormous resistance to acceleration that we call mass. Much more mass in this guy. And mass is measured pretty universally in kilograms. Kilogram is the unit of mass. It's how hard something is to accelerate, or equivalently, the measure of the object's inertia. You okay with that? So when you go to the store, well, I won't do the store thing. You typically buy stuff by mass. It's the best choice. There are other things you can buy by volume. You can buy by other things, but mass is the one that's rock solid. It turns out the mass of an object is the same here as it is on the moon, as it is anywhere in the universe. So it's really a nice, well-defined value. And just to remind you, my shorthand way of describing how do you measure mass? Shake something. Because in the act of shaking it, you're making it go from toward you, away from you, toward you, away from you. What am I doing? Yeah. Or from your view, it's left, right, left, right, left, right. I'm making it accelerate lots of times by way of big forces because this has got a lot of mass. In order to get any decent acceleration out of it, you have to exert a big force. That's sort of Newton's second law, which I hope you collected from the lecture video. It's the observation that an object if you push on an object and you're the only thing pushing, so you're the net force, it'll accelerate. And its acceleration will be in the direction of your force, and it will be equal to the force you exert divided by the mass of the object. Simple as that. So that's why big objects like the bowling ball, which have a lot of mass, don't accelerate much for a given force. They're just, that mass part that's dividing the force is big. So the acceleration that results is small. Is it possible to change directions along one axis without hitting zero, and then without adding velocity on another axis? The second one ties my hands. If you're not allowed to add velocity on other axes, I'm stuck. But let me try this story. That suppose I'm heading to your left, and I want to head to the right, but I do not want to come momentarily to a stop. If I accelerate dead straight backwards, I will come to a stop momentarily, and then I'll reverse. But if I don't want it to come to a stop, is there any way I can reverse directions? And the answer is sure. Here, I'm going to head off to the left, and then I'm going to change the direction of my velocity. And now I'm reversing. I never came to a stop. I was going the same speed the whole time, actually. But I simply turned, and that involves acceleration, but I accelerated to the side. So if I show you here's my hand showing acceleration. So if I was going along, let me get started. Okay, I picked up some speed. Now I'm going to accelerate to the side, and now I'm going to stop accelerating. I was able to turn around and head backwards without ever stopping, and you do it all the time. All right? If I'm not allowed to go into other directions, other than exactly along this railroad track, there's no way I can't reverse without stopping. So a train cannot go from heading north to heading south on its tracks without there being a moment when it's motionless. Okay. So that brings us then out of skating into the world of falling balls. And falling balls is a topic, I probably taught this since the beginning of this class. And what it's doing is it's looking at the first force, or a first force. the simplest of the forces. Because up until now, I've talked generically about, yeah, a force causes acceleration, and that's the way things are. But how about we pick a force, name it. So I'll name it. It's the force on a ball. I'm being a little picky here. So have the ball in mind. The force on the ball due to the Earth's gravity, due to the Earth. And so it's the same. There's a single force on this ball that we're talking about. It's got a couple of names. It could be the gravitational force on the ball, in parentheses, due to the Earth. It could also just be the ball's weight. That's all. So the simplest one is just the ball's weight. And so what does weight mean? It's the force due to gravity on the object. So that's your weight. Whatever your weight is, your weight is specifically is the force that gravity exerts on, the Earth's gravity exerts on you. As an aside, gravity's an interesting force that applies to everything. Everything exerts gravitational forces on everything else. It's always attractive. That is, it always pulls things toward each other. So you're exerting a gravitational force on every other person in this class, attracting them toward you. It's unavoidable. It's super weak, so it's not going to have any influence at parties. And the only thing large enough in our common experience to exert gravitational forces that are noticeable is the Earth. The moon, to a lesser extent, we'll see, and the sun. But it's really the Earth is the only thing with enough oomph to really make a noticeable force on us. So if the Earth pulls down on this ball with a force of about 1.3 newtons or something like that, or equivalently some small fraction, a third of a pound about. It's about right. So it pulls down on this. We'll see pretty soon that forces always come in pairs. They're equally strong in opposite directions. So I'm giving you a heads up in the future. The Earth pulls down on the ball by way of a gravitational force, and that is the ball's weight. Secretly, the ball pulls up on the Earth equally hard. It's a real force. The ball is actually pulling up on the Earth with a force of about a third of a pound. Okay? Same with you. Okay, so that's the ball's weight. Questions about the ball's weight? Force due to gravity. Next point is the ball's weight and the ball's mass are different physical quantities, truly different. And this is why I almost got started talking about the grocery store problem, which is sort of, the grocery store, you can buy things by kilograms, which is mass. And so you take a kilogram of flour, and if it's a kilogram, you know exactly how it's going to accelerate in response to a certain force. Okay? If they're selling it, however, in pounds, pounds are a little messy even. There's more than one type of pound in the American measurement system. But the pound that you're most used to is the force, pound force. How hard is something pushing on you? Oh, it's a 10-pound force pushing on me. Okay? And so if you buy stuff by weight, by pounds, it's a little flaky. And we'll see why in a minute. For the moment, though, I want to make sure it's clear that mass and weight are different. Mass is resistance to acceleration. It has nothing to do with gravity. You can go somewhere in the universe where there's nothing around and gravity is just insignificant, no gravity. It's still going to have a mass. Okay? This ball is still going to be harder to shake than the little ball. You okay with mass? Weight is different. Weight's all about gravity. It's how hard the local gravity is pulling on something. And I'm put in there the local gravity because, this has got a certain weight right here due to the Earth's gravity. But if you go somewhere else, the strength of the Earth's gravity varies with location, and therefore the weight of the ball will vary. And as you go higher up into the mountains or something, or into a plane, or astronaut land, the weight gets less. Furthermore, you can go to different places on Earth, and the Earth is not a perfect sphere. Why do you think the Earth is not a perfect sphere? What's the Earth doing that makes it not like to be a sphere? It's rotating. So it's kind of flung out at the equator. The Earth is wider at the equator by some, I think it's 26 miles, something comes to mind. It's somewhere in that range. So it's wider at the equator. And the consequence of that is that people at the equator are farther from the center. And therefore, the weight they experience is a little less. So if you want to lose weight, you can go to the equator. All right? It's true. You genuinely lose weight. Physicists would all agree. You don't want to go to the North or South Pole. You're particularly heavy. Yeah?
Do we know, like, is it a measurable amount? Do we know roughly?
Oh, yeah. Is it a measurable amount? Yeah, it's about 0.5%. So it's significant. So you want to, if you weigh 200 pounds and you want to lose a pound, shift from the North Pole where you were weighed last to the equator. The equator actually has an added feature that is because you're rotating, you got some inertial character to your behavior. And when you stand on a scale, the scale doesn't quite have to support you properly. This is sort of a complicated side that I hope you can follow. But if the Earth were spinning fast enough, you know what would happen. You'd be flung off of it, just like whipping something around in a circle and letting go. So you're being flung a little bit out too. And as a result, when you stand on a scale, it doesn't read your full weight. The flinging effect lightens the burden on the scale in a way that we could talk about when we talk about how spring scales work. So there's another 0.5% that comes from that. So the scale will read 1% lighter on the equator than it does on the poles. So these are not, it's not insignificant effect. It might not bother, you have to be pretty picky to worry about 1% of your weight, but this will really affect some things like clocks. Like we'll talk eventually about pendulum clocks, grandfather clocks, wall clocks, tick-tock, those guys. They depend on gravity. If there's no gravity, that pendulum doesn't swing back and forth. So they need it. Furthermore, they're dependent on its strength. So if the gravity changes, like you move the clock to the equator, it won't run right. It'll keep bad time. You have to adjust for it. Yeah?
So what do you have to do in order to get an accurate measurement of how much you weigh between the equator and the poles?
So what do you have to do to get an accurate measurement of how much you weigh between the equator and the poles? The answer is don't sell anything, or including yourself, by weight. Weight is iffy. If you go to the moon's gravity on the surface is only 1/6 of what it is here. So if you take a whole package of Oreos to the moon, it was 1 pound on Earth, it's only 1/6 of a pound on the moon. You can eat the whole thing, it's the same calories. You don't fool yourself. It's not like, oh, I only ate 2 ounces. What matters is how much is there, the substance, and mass is the better measure. Weight is flaky because it changes with location. You okay with that? I mean, the key thing to take away from this, 2 different physical quantities. We use them somewhat interchangeably in modern life, but be careful with them. One's a force, weight, and one of them is a resistance to acceleration, mass. Okay? In fact, the balances, as opposed to scales, when they weigh in someone for a sporting event, they make a mass measurement. I mean, it's complicated how they do it, but they ultimately measure mass because that's the only thing reliable. Otherwise, you can be off by 1% pretty easily. All right? What else? Second observation is, although mass and weight, I can get lost and turn this into a lecture. I don't quite want to do that. Let me see. Ding. Let me ask you all this question to sort of see whether you're all on board here. I will actually start the clock. Yeah, you can put. Oh, the frequency code was AA. Yeah, we're good. AA. Everybody AA. All right. Oh, did I botch the job? All right. So the question is, a quarter, a U.S. quarter, and a U.S. dime. They're different. Compare their masses and their weights. This is not a hard question. I'll give you 30 seconds and we'll do it. This is almost sort of a warm-up question. 5, 4, 3, 2.5, 1. Okay, I'll call it a day. Here we go. And the answer is overwhelmingly D, which is the quarter has more mass and more weight, and that is correct. You'll notice that what's worth noting there is the quarter's got more mass, which means it's harder to shake, and it's got more weight, which means that it's pulled downward harder by gravity. They seem to go together, which is kind of cool, and it's not trivial that situation. Let me try this one. On the moon, a baseball's mass is, so now compare, you leave the Earth, you go to the moon, and now what happens to its mass and what happens to its weight? And again, you can talk about these among yourselves if you want to. All right, I'll call it at the 30-second point here. Three, 2, 1. Yay! Oh, that's pretty good. Never happens. 100%. 100% right. You all are great. Woohoo! Yes. When you go to the moon or anywhere else in the universe, the weight's going to change because the gravity's going to be different. But the mass, not always the same. As a related aside, when astronauts are out and about, how do you determine how much astronaut there is? I mean, they do care about this because one of the biggest motivators for the space program is one thing they study the most is to study what happens to astronauts in the space program. It's a little bit self-referential, but anyway, they want to know how an astronaut changes with time. And you can't weigh them for various reasons. And the weighing is all flaky anyway because gravity's an issue. Where are you weighing them? And so they measure mass. So historically, they have had jigs that would shake the astronaut. The astronaut would grab onto these gadgets and try to be as rigid as possible. And then the thing would shake them back and forth, just like I do with the ball, to find out how much mass there is. That's what you got to do. Anyway, so leave weight aside. If you're doing intergalactic trade, don't sell your cookies by weight. Sell them by mass. Okay, so where I want to head next with that is that I didn't mention that mass and weight, although they're completely different physical quantities, they're proportional to one another at a given location, which is a really weird thing. I mean, you may just completely take it for granted. But this ball has a small mass and a small weight. And this ball has a big mass and a big weight. And if you divide one by the other, weight by mass, it's the same, you come up with the same result for the two balls. Exactly the same result. And that connection is, it may seem like no big deal, but that's the part of the connection that led Einstein to develop the theory of general relativity. So it was a huge to-do at the beginning of last century, and it has huge consequences for our understanding of the world universe. That aside, though, for our practical purposes, it has a very interesting effect, and that is, it means that if you take, I'm not going to drop the bowling ball, I've done it, it's happened by accident over the years, and it's the people downstairs that come upstairs and wonder what the hell hit the ceiling that's a problem. But the consequences of that observation, that an object's weight is exactly proportional to its mass, they go together. Double the mass, you double the weight, exactly. That has an interesting effect. Which of these two balls is going to hit the floor first when I drop them together? Same time, yeah. I can do this as a clicker question. You get another 100%. They're going to hit together. Poof. That's falling. Just, to pin it down, I did it in a lecture video. I'll do it again here. Just falling. What falling means is that if it's you falling, that you're experiencing only one force, your weight. Equivalent, you could be experiencing something else, but the net force of everything else has to go to 0. So the only thing that matters is your weight. So a ball that's experiencing only its weight falls. And in that means that it experiences a downward force toward the dead center of the Earth, I should be careful, toward the center of the Earth, and it accelerates downward. Furthermore, the strength of that force, it does vary with distance from the center of the Earth, but very slowly. So for all practical purposes, the force here and here and here is the same, so the acceleration during falling is the same. You'd have to fall a huge distance for gravity to change enough that we would say, your acceleration is changing. So a falling object not only experiences just one force, its weight, but its acceleration is constant, steady, straight down. What is its acceleration? It happens to be this universal constant here near the surface of the Earth of 9.8 meters per second squared. The meters per second squared is, alas, the unit of acceleration. If it doesn't make a lot of sense, we can work on it. But 9.8 of those units is what's going on. In the American system, that's about 32 feet per second squared. So what that means then is that a falling ball acquires more downward velocity at a rate of 9.8 meters per second squared. With every second, it gets almost 10 more meters per second downward. And it accumulates. Or initial 32 feet per second downwards, and it accumulates. So after 1 second of falling, the ball is moving at 10 meters per second downward. At 2 seconds of falling, it's falling 20 meters per second downward. 3 seconds of falling, it's falling at 30 meters per second downward. Is that okay? Okay. So, and it doesn't depend on what the ball looks like. Any ball will do, with the exception of wiffle balls and Nerf balls and stuff. Let's see. Oh, well, I mean, I basically asked that. Okay, if you get rid of air resistance, with a sheet of paper is a problem. If I drop a sheet of paper and a ball, the sheet of paper loses. So if I could get rid of air resistance, how would things turn out? Would they fall together or not? You tell me. I like to ask simple questions sometimes. Who cares? All right. 5, 4, 3, 2, 1. Ta-da! Okay. Yay. Few of you are skeptical. So there's 7% skeptics saying, no, the paper will not fall the same as the ball. So if I want to get rid of the air resistance on a sheet of paper and let it fall the way it wants to fall in the absence of air resistance, can you think of a way of doing that? How would I get rid of the air resistance on the ball, other than like take all the air out of this room, which would be exciting? If I decrease the surface area, that would work too. If I compress this into a little teeny pellet, which would take a while, that would work. Yeah, Emily? Yes, so Emily's observation, put the paper on top of the book, and they are not attached to one another. The book is not going to pull the paper down. It's simply going to get the air out of the way. Okay? So it's the poor man's version of they have the fancy gadgets that take the vacuum and let the feather fall. Just get the air out of the way. Okay? Okay, so everything falls together, absent air resistance. And really, this whole first couple of days, I've been trying to bury the nuisances, friction and air resistance being the most famous ones. So we're trying to see how things move in sort of the absence of those nuisances. We'll bring them back eventually, in fact, pretty soon. Okay, so falling balls, they accelerate downward. I talked in the lecture video about how where the balls are located at various moments in time, I do want to remind you of the fact that the balls, when I drop it like this, so-called drop from rest, which is physics jargon that I'm so used to saying, and physicists are so used to, but hopefully it's clear to you that dropping something from rest means that you start with it motionless and let go, and it accelerates downward. Its acceleration is steady the whole way. Why? Because the force on it's steady. It's its weight. So acceleration is constant. On the other hand, the velocity is increasing steadily. It's going faster and faster in a downward direction. That should be fairly followable. The third part is a little more subtle. Where is the ball? Well, because it's traveling faster and faster with each second of fall, it covers more distance with each second of fall. And therefore, if you look at sort of the halfway point in time of where the ball is located, it's not the halfway point in space. During the first half of the fall, it doesn't travel very far because its average speed was low. During the second half of the fall, it traveled a lot farther. So falling objects, if you want to look for falling objects halfway through their fall, that's halfway in time, look high. Look for them up near where they were dropped from. It's in the second half of their fall that they travel the most distance. And if you're a diver, you've seen this. Well, watch people diving. That second half, they pick up a lot of speed. They cover a huge distance in the second half of the fall. It's okay? Ooh, I'm getting way behind on my... How do you measure mass so it's the same everywhere? You measure mass by looking at exerting a force on something and watching its acceleration. Those aren't trivial things to do. Pushing reliably with a force of 1 pound or 1 Newton is a little tricky, but you can do it. And watching the object's acceleration is a little tricky. You gotta watch its motion very carefully, but you can do it. And if you do that with a 1 kilogram bag of flour, it's going to be the same here as anywhere in the universe. Isn't there a terminal velocity at which an object stops accelerating? And the answer is there typically is a terminal velocity. And what is terminal velocity? We'll see this when we come to talking about air and air resistance. When I drop a ball, at first it moves through the air quite slowly, and the air is really insignificant in its effect on the ball. There's a little bit of a buoyancy effect too, like a helium balloon floats in air. The ball is not oblivious to the air around it, and it is actually being helped, supported a little bit by the air. That's another point we'll come to. But the one that's relevant here is when the ball is moving through the air, if it's moving slowly, it barely notices. But as it goes faster and faster, the air begins to come, it's rushing up at it. From the ball's perspective, be a fly on the ball. Woo, the air's coming up at me, man. It's getting windy. And the faster the ball descends, the more that upward breeze affects the ball. And there will come a point, if we drop it from high enough, where that upward breeze will cancel the ball's weight. So the ball will not be a falling ball anymore. It won't be experiencing only one force, its weight. It will be experiencing 2 forces, its weight downward and an upward push from the air resistance. And that upward push will eventually become as strong as the weight, and they'll sum to 0. And the ball will come down at a steady pace, the so-called terminal velocity. So that's what terminal velocity means. It means when you're falling and you have reached the point where the air resistance is so big that it equals your weight. And any of you who have done parachute jumping, skydiving, not something I've done or will do. I believe too much in gravity, or just risk averse. Anyway, if you've done this, I thought that you would feel weightless and interesting things the whole way down, but in fact you don't. During the first moments stepping out of a plane, things are complicated because you were in a moving plane, but pretty soon you're plummeting downward faster and faster and faster, and you hit terminal velocity. For humans, for us, the terminal velocity is typically between 100 miles an hour and 200 miles an hour, depending on your shape. So if you pull into a tight tuck, you can go to, or I don't know how you do it, you can get to 200 miles an hour, but mostly you're more like 150 or something. If you're out like this, it's like 150. And you come down steadily. Is that okay? And that's terminal velocity. It's an air resistance problem. Does 9.8 meters per second squared ever plateau at a certain speed and stop accelerating? The 9.8 meters per second of acceleration is the acceleration due to gravity, and it never stops in the absence of air resistance. If you have air resistance, that acceleration is no longer relevant. You're accelerating a little less because you've got an extra force on you. And eventually, with the terminal velocity, you reach no acceleration. All right, let's see. Is there a term for the change in acceleration over time? That's an exotic one, and there is a name for it, and I'll have to remember it. It's like jerk. It's called jerk. We will never deal with it. Leave the jerks alone. Can you drop the paper on the ball again? For those of you who missed it, ready. Okay? The book got the air out of the way and allowed the paper to do what it was planning on doing. Incidentally, again, this class is about being relevant for you all. Just help you. The paper, you could say the paper was drafting the book. For those of you who do any sports where you're chasing somebody, running, swimming, bicycling, air resistance matters. So when it's an extra force causing a nuisance. So if you're trying to run along at constant velocity, Usain Bolt running along at constant velocity, he still has to get the ground to push him forward the whole way, even though he's going at constant velocity. He should be able to coast. What's the problem? He's experiencing air resistance. If you could get rid of the air resistance, he would no longer have to be pushed forward at all. He would coast. And so getting rid of air resistance is a big deal for all these high-speed sports. And the easiest way to do that is to move behind somebody else who is getting the air out of the way for you. So look at all the track bicycling and open bicycling. Drafting is a huge deal. It's illegal in certain sports because it's a huge advantage for the person behind. It's allowed in other sports because you have to trade off. The lead person does all the effort. So this is it's an illustration. If you get rid of the air resistance, you basically allow the paper to draft. The paper can fall properly. Let me see if there's anything left that I really want to make sure you know about falling balls. I would do want to do this, that the ball, when it's going up, is still falling. It's still accelerating downward at the famous acceleration due to gravity, 9.8 meters per second squared. The fact that it's moving upward is just history. It just has to do with the fact that I threw it up initially. And when it's up on its way up, the only force acting on it is still gravity. It has nothing to do with me. It's experiencing only its weight. It's accelerating straight down. I will come back and say 2 cents on Wednesday to talk about this motion, the motion of the ball going up at an angle, because there are some details that I didn't include in the video and like to pin down. All right, see you on Wednesday.